guys, and welcome to this one. This is another episode, and this time around we're going to be looking at maze or a maze problem. We're still on the recursion series, so basically this is just a maze problem that makes use of backtracking and yeah, basically my backtracking technique to like execute some the backtracking technique to execute some kind of values in a sense, right? So what do we do here? So we say the goal is to start from a given point and search through the maze until we reach the destination point. The main idea is to use a depth first search. So basically what that means is that we are going to be searching through, you know, a path, and if it's not successful we come back and search another path, and this will make sense subsequently. So don't try to disturb yourself too much about it. DFS approach: we keep moving deeper into one possible path until we either find the destination or hit a dead end. When we hit a dead end, we track back by popping the last position of the path and trying another available direction. This process continues until a valid path to the end is found or all possible paths have been explored. Okay, I think that's it. So we say maze runner. That's just my naming convention. So what does it take in? It takes in a maze that is a list of lists where the outer list holds an inner list and the inner list holds integers. And then we have our start coordinate, which is comes in form of a tuple of two integers, and our end tuple, which comes in the form of two integers. Basically, to like maybe highlight this question in a sense, if I could use this spot, I think I will get there. So this stipulates the direction, and we make use of lists within a list, hence meaning that O of 1 will be the outer list at index of O, and an inner list or sublist at index of 1. So O of O is the x-axis and 1 is the y-axis, as should be. So giving an example, I think to make this more palatable or to make it more visual, right? So we can take it to be something like this, right? Where we would have it here. So you could see that this is a list within a these are lists within a list, and this is the first index, the second index, the third index, and uh, looking at it in that manner, we could see that these are the rows and these are the columns. So in sense of like maybe assessing maybe one of these guys, if I say 1 comma 0, basically I'm saying list at the index of 1 and value at the index of 0, right? So basically you can see here 0 and 1 is 0 comma 1, which is this guy, which is 0, 0 comma 2, which is now 1. So basically that's what we that's what we have, right? And that's how we are going to be going through it. And basically, to explain the problem more, what we are being told is that we are going to be given maybe a start index, maybe let's say maybe 0 and 1, and we are going to be told to get to the index of 2 and 2 here, right, which is what we are going to try to do. So any place where we have 1 will be determined to be a wall, and any place where we would have maybe that is going to be out of the bounds, we're not going to also consider it. So basically that's what we are being tried to do. Then in sense in an attempt to explain the depth search, so let's say we start here, right, and we go to the right. When we go to the right and we try to go to the right again, it's going to tell us, oh, this is a wall, so we are going to track back. If we want to go to the right and go down, it will tell us this is a wall, track back. If you want to go back, it's going to tell us visited, so we track back as well to the point where we said, oh, let us go right. And we are not going to go right anymore. Now we're going to go down. Now, if we go down, we go to the left, it's going to tell us, oh, this is out of bounds. Go to the right, it's going to tell us, oh, this is a wall. Go back, this has been visited. Go down, there is an open wall there, an open space there. So we go down. The same thing when we go down, we make this, directional checks. Same thing again, we go to the left up until we now get to this end point, and when we get to this end point, we are going to say, oh, we are here, and we can then return through and stuff like that. Now, moving forward, we first establish our directions, basically where we have this minus 1 and 0 as up, this as down. So minus 1 would be changing the row going up, and down would be going down, and with your column remaining the same. Left, the same thing. Your left, you're going to the left, that's minus 1 in this thing in your column space, and your zero row space remaining the same. Your right, the same thing. You go to the right, plus 1, and your column space and your row space remaining the same. So that's just what we instantiated there. Now, say we accept the rule as earlier stated, the index of the outer list. I don't think this is earlier. So we say we accept the rule as earlier stated, the index of the outer list. So basically, we know that our row is these guys. So whatever the index whatever the amount of index is going to be the row count. That's the maximum amount of rows. Like for this illustration now, we know that we're having a row count of 2. That's if you're counting from 0, 1, 2, 3, right? So 0, 1, 2, right? So that's our row count, and that should also be our column count. So, but we say length is equal to maze bracket 0, length of maze bracket 0 if row count is greater than 0. So we are going to consider our row count, since our column is dependent on our row. So if we don't have any guys here or any lists here, we won't be having any columns, right? We won't be having any other lists to now call it to say, oh, this is column 1, column 2. So basically we make it dependent on our row count for that reason. So if none of it exists, then we have 0 this thing. Now moving forward, see here we write a function that will check relative comma relative to the pause has come be things, right? Relative to the present location of navigation. So basically what we are trying to say, that we are going to read this function, we're talking about this function here now. We are saying that we write a function that will check relative to the present location of navigation when we begin to move across the maze. That's basically depending on where we are in the maze. If our directionings, right, are valid, that's what he's trying to say. He says that is okay. Present location of navigation is even a valid point, node, location, axis, whatever, right? So whatever you choose to call it. If it is out of bounds or the location is a wall, this function will return false. Or if it is a row that has been visited, VC, this my VC, visitor has been, is it the spelling of visited? Yeah, I think that's correct. Visited, yeah. I don't think so. I don't know. before, before, okay, has been visited before. Okay, okay. It checks. Okay, or if it has been visited before, we don't go there. We don't go there again. Now,